Okay. The
Okay.
title of Suvier's talk is Paramagnon Fractionalization Theory of the Cuprate Pseudogap and Phase Diagram. Please.
Okay. Okay, thank you very much, Imada-san. It's a real pleasure to be here. Thank you for the invitation for this very interesting conference. Okay, like many speakers, I'll begin with this famous phase diagram for the cuprates. My focus here will be on the metallic phases, in particular the pseudogap metal. And the idea here is that really we want to understand these higher temperature metallic phases first before we go down and understand all the rich phenomenology at lower temperatures. So if there's one message I want to get across, it's our rather simple understanding of the nature of the pseudogap metal phase. That's going to be the parent for everything else in the phase diagram. And the simple slogan is that you can think of the pseudogap metal as a weakly interacting version of two states of matter that are now very well established. One is the Kondo lattice heavy Fermi liquid that's found in so many heavy fermion compounds like uranium, beryllium-13. And there's quite a non-trivial theory of how that heavy Fermi liquid state is obtained by coupling conduction electron to a lattice of spins. And the other is the spin liquid, which has fractionalization. The Kondo lattice heavy Fermi liquid has no fractionalization. In a spin liquid, there are excitations like spin-ons that carry emergent gauge charges. And there is, I believe, a key aspect of these emergent gauge field that's important for understanding the pseudogap metal. And the spin liquid, experimentally not as well established, but theoretically now certainly very well understood. So we just have to take these very well understood systems and let them interact. And from that, I believe you get a very useful perspective, not just of the pseudogap metal, but in fact the rest of the phase diagram. So I won't have time to go into all the details of the theory of the pseudogap metal. It turns out to be a gauge theory with all these factors, but don't worry about it. I'll give you a very physical picture, I hope, of what's going on in the pseudogap metal state. But once you have this pseudogap metal state, which has fractionalization of a very particular type, then you can ask what happens at lower temperatures. And this is something we are currently working on. And I'll just have hopefully, depending on the time, say a little bit about those ideas. So in particular, at low doping, you can get a transition involving one of these gauge groups, which leads to nail order with hole pockets of the type that Takashi Kondo has seen very clearly in recent experiments. Then, again, by a different route to confinement of the fractionalized excitations, you end up with the charge order and the superconductivity and the pair density wave that we've heard about. And finally, with yet another route that can come out of this parent pseudogap metal, you can also get a strange metal and eventually a Fermi liquid. Okay, so we have many papers on much of this and much work ongoing, and I'll try to give a little flavor of some of our results. Okay, so but let me begin with what I'll spend most of my time on, trying to give a simple physical picture of how I think we should think of the pseudogap metal. So this is work really started with Yahui Zhang. Many of his ideas are his. He's now a junior faculty at Johns Hopkins. And there's students of mine, Alexander Nikolenko, Maria Tekhinovskaya. And we've also collaborated with Dirk Moore and his student, Eric Muscat. Okay, so this is the simple picture of electron fractionalization we often hear about. You have an electron that splits apart into excitations that carry its spin and its charge. That's the basic paradigm of spin-charge separation, which has been used by many, many people, including me, in many hundreds of papers. But there's just one basic problem with this way of thinking about things. this particular excitation, the holon, an excitation that carries charge but no spin, basically has never been seen either theoretically or experimentally. And the reason is really very straightforward. Is the energy scale at which fractionalization happens is J. But once fractionalization has happened, say in this root, then there's a residual attraction between the holon and the spinon, which is much stronger in 2 dimensions than in 1D, and its energy scale is T. So if T is much bigger than J, you can't really expect this holon to survive as an independent excitation. So the route to fractionalization I'm going to advocate is a little different. We start with an electron, and you can take an exciton or a spin exciton or a bound state of an electron in a hole and get the paramagnon, which is an excitation that carries spin 1 and charge 0. So this is, helium-3. We see it in many nearly ferromagnetic metals. I think Bernard Keimer gave some indication of its presence in the cuprate. So the important point is this excitation has charge 0. And this can now fractionalize to spin a half excitation. So it's purely a spin fractionalization. There is no fractionalization of charge and spin. I think that's the key thing we have to keep in mind. So now you can get 2 spin-ons, which carry spin a half and charge 0. And this is what, we know many examples where such things do happen. And our claim does happen in the pseudogap metal of the cuprates. All right, so that's cartoon picture, so let's get to something more specific. So how do we get a theory of paramagnons? I'm just going to rewrite the theory in a slightly different way. So one way you get it is you start with the Hubbard model, and you decouple the Hubbard interaction term. First you write it as S squared, and then you introduce a conjugate field phi, which is the paramagnon field, which couples linearly to the spin density, and you do a phi squared term here. So up to this point, this is all completely exact. It's just rewriting of the Hubbard model to free electrons coupled to a boson phi, which has spin 1 and charge 0. Okay, now I want to give this boson a little bit of dynamics, just so that I can talk about its states. So imagine I integrate out some high energy electrons, and then I can rewrite the system as shown pictorial in this very simple picture. These are 2 equivalent systems. You could have the electrons with the Hubbard model, or you could have free electrons coupled to a rotor or a particle that lives on a sphere. And that's simply coming from this kinetic energy for the particle and the potential for the particle that I assume generates after some renormalization. And there's a coupling lambda between the electrons and this particle phi. Okay, so now because of these kinetic energy terms, I can now look at the spectrum of phi. And a very natural spectrum for phi is that there's a singlet ground state and a triplet first excited state. So then what I can do is I can just replace this phi by a pair of spinor halves. So this is really, again, essentially exact, apart from some high energy states I'm not interested in. So each such rung of spins has a singlet ground state and a first excited state J perp. And now this double layer antiferromagnet with the rung coupling J perp is coupled to free electrons with coupling lambda. Okay. And this is essentially a rewriting of the paramagnon theory. So I'm just playing games right now and writing down a well-known theory in a slightly different Hamiltonian form. Okay. In particular, the phi is the operator that takes you from a singlet to a triplet. And so the paramagnon is this excitation. So there's a rung triplet excitation, which is my paramagnon, and it's coupled to free electrons. And we can also see that the phi operator then is the operator that takes you from the singlet to the triplet, which is S1 minus S2. So now I have the nearly final form of what I want to talk about. I have a 3-layer system. I have free electrons in the top layer, and then I have spinor halves in the second and third layers. They're coupled to each other by this coupling J perp. And then there's a coupling between the physical electron in the first layer, which is antiferromagnetic. It's like a condo coupling, and it is antiferromagnetic. And the coupling from the first layer to the bottom layer is ferromagnetic. That's coming from the opposite sign over here, which is J tilde K. Okay. And now, this is the motivation from the usual theory. Now I can just forget about all of that and just look at this model on its own terms. And in the limit where J perp is very large, this is just a rewriting of the Hubbard model. So if I do the Schrieffer-Wolff transformation and get rid of the Rung triplet states, then this model is just the Hubbard model, with the Hubbard repulsion GK squared over J perp. That's really a simple exercise. You can just work it out. Okay, so all I've done so far is rewrite the Hubbard model. And this mapping is, of course, only valid when J perp is much bigger than JK. Now, if I take the limit of J perp become the J perp, I put these spins into singlets. I'm back to where I started. I don't have any useful new phase of matter. But now I realize that there's another interesting thing that could happen. We know that for the single spin Kondo problem, JK, if it's antiferromagnetic, under RG goes to infinity. Whereas the ferromagnetic JK will flow to 0. So let's imagine, even though we start out with JK being smaller than J perp, that after some RG, JK has become large. And what is the fate of this system when JK is large? Well, that's exactly where you get the pseudogap phase. So let me show you the simple picture of what happens. So when JK is large, the top two layers are your Kondo lattice. So we know if I have, and you forget about the bottom layer with coupling J tilde for a moment, then the top layer is just a Kondo lattice, and a Kondo lattice forms a heavy Fermi liquid state. Now, what is the size of the Fermi surface in a heavy Fermi liquid state? It's the density of the electrons plus the density of the spins. Here, the density of the holes is 1 plus p. The density of the holes here is 1. So the total density, the large Fermi surface, has size 2 plus p. But you only measure things modulo 2 for Fermi surfaces, so it's p. So in fact, here, the heavy Fermi liquid Fermi surface is small. And that's the pocket Fermi surfaces of the pseudogap metal. But you can't forget about the bottom layer. It's still there, and it must form a spin liquid or break some symmetry. But if you broke some symmetry, then you're in some ordered state. So you do have a spin liquid with fractionalization in the bottom layer. And this is important for various consistency and general Luttinger arguments. Okay, so that's the theory of the pseudogap. To summarize, here's another picture of it. The top two layers form a heavy Fermi liquid, and the bottom layer forms a spin liquid. And if you want a trial wave function, it's very simple. You take the trial wave function for the heavy Fermi liquid, which is just a Slater determinant of C and F1. And then you take your favorite spin liquid on the layer S2, could be any spin liquid, and then you take this wave function and you project everything on the bottom two layers into a Rung singlet. So this is a wave function only of the physical electrons, and that's your trial state for the pseudogap metal. Now, it'd be great if somebody, with all the technology for projected wave function, if someone can work with this. We haven't quite succeeded, although we've tried. It's numerically a bit challenging to work with this. So this is what you get as a function of JK over J perp. You get a pseudogap metal here. And then when JK becomes much bigger than J perp, much smaller than J perp, that's this side, then these two just form a singlet. So that's the spin liquid, and there's your spin singlet. That's the Fermi liquid. So the bottom line is you have a spin, the pseudogap metal is a Kondo lattice heavy Fermi liquid plus a spin liquid. and the Fermi liquid is where these round singlets just disappear and can be integrated out. All right, so that's the simple picture. And now we can use this, of course, make this into a real gauge theory and do lots of calculation. But the physical idea, hopefully, I have gotten across by now. All right, so we've done a lot of calculations. In particular, one of the things you can do is try to look at the photo emission spectrum for the electrons in the pseudogap phase. So that's the phase where you can pretty much ignore, to leading order, the spin liquid at the bottom, and you just take the theory of the heavy Fermi liquid, which we know in the heavy Fermi liquid you have a hybridization B that couples the physical electron to the spins, the spin-ons, the fermion, the F electrons. And now in this theory, the free parameters are T1 and B, and from which you can fit the data. In fact, I don't really need to go into this in any detail because a lot of this has been discussed already yesterday and earlier, and also way back by Imada-san and many of his collaborators. Sakai gave a very nice talk. And so there are similarities to these dark fermion theories or the YRZ theory. At this level of the mean field theory, they're essentially the same. Once you get beyond this, then in our approach, we have to really worry about the fractionalization on the second layer. They have somewhat different ways of thinking about it using DMFT. Okay, so for example, you can get these hole-like pockets with very low intensity on the back. And presumably that's an explanation of what's going on in photo emission. There is at least one claim by Peter Johnson's group of indeed the pockets. What happened to my, yeah, there is, what happened, yeah, of the back side of the pocket, at least some indication. But it may well be because at higher temperatures and because of disorder, this backside is going to be very hard to see eventually. You can also look at the antinodal spectrum, where there's beautiful data by ZX Shen, and that can also be mapped on, explained very nicely in this very simple model. We've also done some modeling. This was the work with Dirk Moore of the MDC and the EDC and the antinodes, and that required us to look at damping coming from this ancilla, second ancilla layer of a spin liquid. All right, so that's a summary. I guess I'm making good time of the pseudogap metal. And in the end, it's really extremely simple. We can think of it as a Kondo lattice heavy Fermi liquid along with a spectator spin liquid. Okay, and certainly for the photo emission, this does a very good job of explaining the observations. So now we want to ask, what happens as you lower the temperature? Now, it would be very nice if the spin liquid survived down to 0 temperature. Then you would have really a new state of matter that you can celebrate. But as far as we can tell, and also in many theories, that doesn't happen. The spin liquid, the fractionalization disappears, and you get more conventional states. But the onset of these more conventional states is very different from Fermi liquid theory. It's not some Fermi surface instability. It's much more complicated. It's really a confinement transition in some gauge theory. And so we're working hard in understanding the nature of these confinement transitions. So I'll say a few little, I have 15 minutes, so I can say more about the possible confinement routes. So one route is to just get the Néel order with pi. Is that correct? I had 35 when I started, and I have 15. Huh? Sorry? Correct, yes. Okay, so I have about 15 minutes to talk, I believe. So what about just the Néel order? Well, that turns out to be relatively simple because you just have to condense a spin-on at this wave vector. And this is discussed in our recent paper. And so then this state here is what has been seen very clearly in this paper by Takeshi Kondo et al. where you've got a commensurate antiferromagnet in a doped state, and they clearly see the hole pockets, even the backside centered at pi by 2 in the Brillouin zone. So in this theory, we can now watch the evolution of the pseudogap hole pocket, which is here, to the nail hole pocket, which is over here. So they have roughly the same size, but there's an important difference, which is perhaps clearer in these two pictures. So here, what you see is that the hole pocket has its backside right at the Brillouin zone. It's like it's more shaped like a half moon. And it's not centered. The center of this pocket is not at pi by 2. Whereas in the nail state, it's exactly at pi by 2 centered, and the back and symmetric. And if you took the full size, it's twice as large as this size that you get in the pseudogap. So, and we can follow the evolution between them, and it'd be very interesting if someday this could really be studied in experiments. So that's one of the main things that come out of this analysis. How does the pseudogap Fermi surface evolve into the nail-ordered Fermi surface? Okay. Next, we can think about what about the things we've just heard about, which is superconductivity and charge density wave, and yesterday from Seamus, pair density wave. Okay, this is something we're still working on with my students, Maine Christos and Henry Shackleton, and postdoc Giusilio. And I'll just give you a little bit of our ideas. So here, what we want to do is really think about condensing a boson that carries some of these quantum numbers, so that you lose the emergent gauge fields and confine them completely. Now, so the way we're going to do it is to use the Schwinger fermion representation. Now, in some very nice work by Chong Wang et al., it's now become clear that the Schwinger fermion approach in the pi flux phase is in fact exactly dual to the Schwinger boson approach, which gave the CP1 theory, which we used for the nail order. So these are really the same theory, but at the level of mean field theory, one may be more convenient than the other. So to get the charge order, we use the Schwinger fermion approach in the pi flux phase. And then you have to condense some boson that carries the SU2 gauge charge in this SU2 theory. And the most natural boson is, in fact, just the hybridization and the pairing of the fermions in the first and the second layer. These are the ancilla fermions. And then you can try to write down some Landau potential for this boson, consistent with the constraints of gauge invariance and also the various symmetries of the theory. So this turns out to be very interesting, and we can already see that you get exactly the type of phases that are actually observed. Also, this may be reminiscent of things you've heard about in, say, in the RMP article of Li, Nagaosa, and Wen, where they used exactly the same pi-flux mean field theory as a starting point. But anyway, I don't know for sure, but it seems to us right now that they didn't really treat the full symmetry structure of the boson action correctly. And once you do, you in fact get D-wave superconductivity and many other possibilities coming out. Anyway, so this is very much work in progress. All right, so finally, let me talk about another piece of work that we have been involved with in recent years, which is how do you go from this pseudogap metal or to the strange metal via the Fermi liquid. So there's two steps to this. One is you try to write down some gauge theory as you go from the pseudogap phase to a large Fermi surface. This was done in these papers by Yaoi Zhang. And then you try to look at the fluctuations in this gauge theory and see if they give you anything like a strange metal phase. So what we have realized recently in this paper with Avishkar Patel, How You Go, and Ilya Estolets, is that there's actually a very universal theory of strange metals. One example of this would be this one, but there are many others, including the whole class of Hertz-Millis theories. They can all give you essentially the same strange metal, with one, and requires basically two essential features. One is that you have a two-dimensional metal with some critical boson, some low energy collective mode. And two, that the coupling of the fermions to the boson, which we call the Yukawa coupling, is spatially random. So there has to be some randomness in the interactions. And that turns out quite universally to give you a strange metal. So I have 10 minutes to describe that strange metal. All right, so in particular, there's a number of characteristics of strange metal that have been discussed in the recent literature. Here I'm defining a strange metal as any material whose resistivity is linear in temperature, and it's also small, smaller than h over e squared. When the resistivity is larger than this, we call that a bad metal, and I won't talk about that. As emphasized in this article by Andy McKinsey and Sean Hartnell, almost all strange metals seem to have a T-lock T-specific heat. So Dirk van der Merel, I thought he'd talk about this, has been looking at optical data in YBCO in particular, I think. And a reanalysis of older data has led to this form for the optical conductivity. Basically, there's a transport scattering rate, which scales linearly in frequency or temperature. But there's an effective mass that, because of the Kramers Kronig of this linear frequency dependence, has a logarithmic dependence on frequency and temperature. And if you take this form, it actually gives a very good fit to frequency and temperature dependence of the optical conductivity. And then there's also observations by Dan Dassault of the electron spectrum and on the nodal region, and you get, again, alpha close to 1/2, at least near optimal doping. And that would be what's called the marginal Fermi liquid spectrum, where the scattering rate is either linear in temperature or linear in frequency, whichever is larger. So I'm going to now present a theory which has all of these four features. And it's a very general theory, as I've emphasized. In particular, would apply to this phase diagram I've just discussed. So what are the ingredients of the theory? So first of all, you need a two-dimensional Fermi surface. Then you have some strong interactions. So I've just put all the R's to be the same. There's going to be various other factors here that, for simplicity, I'm ignoring. Okay. So what we normally do is we take the strong interaction and write it in terms of the fermions coupled to some boson. And the boson has some coupling J. So this boson could be, say, the Ising nematic order. It could be the charge density wave order. It could be the Higgs field in your favorite gauge theory of a Kondo lattice, and so on. Okay, so now we have a theory of fermions coupled to some generic boson. Okay, so this kind of theory in the limit where everything is at long wavelengths has been studied a lot. And in particular, it's known to be a non-Fermi liquid with a self-energy which is omega to the 2/3, probably first pointed out by Patrick Lee. All right, but so it is it's a non-Fermi liquid, but now the question becomes, what does the transport properties look like? So the transport in the end turned out to be rather boring. First of all, this theory has no disorder, so the conductivity is actually infinite. There's a delta function at 0 frequency in this continuum limit. Well, you might then think that there is some omega to the 2/3 contribution, which was computed, but not completely in a lot of early work. If you actually compute its coefficient carefully, you find that it's 0. So in fact, the transport of this non-Fermi liquid is like a perfect metal. It's really not a strange metal. All right, so you say, okay, you've got to put in some disorder. So the first thing you might imagine, you put in some random potential, which scatters the fermion. But this turns out not to be enough. So what we have to do is actually put in random interactions. So there's plenty of evidence for random interactions in STM data of various types, including many by Seamus, where you have lots of randomness and some local energy gap. And this kind of randomness in the local energy gap will only come from randomness in an interaction parameter. So we imagine there's some randomness, perhaps in the 1,2,4 compound that Bernhard just talked about is due to the incommensurations of the charge density wave. So this coupling J also has a random piece, J prime. Okay, so now what I'm going to do is I'm going to take this phi field and rescale it and put the randomness in the Yukawa coupling G over here. So this is our final theory. You have conduction electrons coupled to a Fermi surface. Some electrons on a Fermi surface. And you have a boson phi, which has a Yukawa coupling to the fermions. And the Yukawa coupling has a random piece and a uniform piece. And the potential also has a random piece. Okay, the most important is this G prime term. The prime doesn't indicate a derivative. It's just some fluctuations in the local value of the coupling. All right, so this is the theory that we can solve using various methods we've learned from the SYK model. You could also try to put it on a computer and study it. That's something ongoing by Avishkar Patel right now. And that looks very promising. So let me tell you, what you get from this theory. First of all, the boson Green's function near the quantum critical point has a diffusive form, q squared plus mod omega. And that's not surprising and been known for a long time, probably going back to Halperin, Lee, and Reed's paper on the nu equals 1/2 metallic state. Okay. Then the electron self-energy has various terms, which are interesting to look at. One is just the potential scattering. This is the usual Drude scattering rate, tau, proportional to the random potential V squared. Then you also get a marginal Fermi liquid self-energy. And this has two contributions, one coming from the combination of G and V, the random potential and the non-random interaction. That gives you a marginal Fermi liquid self-energy. But the G prime also gives you the same omega log omega. So this self-energy implies that the inelastic scattering rate is linear in frequency or temperature, as you would want it to be, of course, from the photoemission experiments. And it has two contributions, one from G and one from G prime. All right, so then let's compute conductivity. So there you have to evaluate some set of graphs that are given the so-called Markey-Thompson and Aslamazov-Larkin graphs, and we've done this in great detail. Well, I should say we, it's really Avishkar Patel, how you go and Ilya Estlis have done all the hard work, and you get some very remarkable results. So you get a conductivity which has exactly the form that Dirk van der Merel has postulated from recent analysis of the data. There's a transport scattering rate, which is linear in frequency or temperature. And there's an effective mass, which has a logarithmic divergent in frequency or temperature. But when you compare this transport scattering rate with the inelastic scattering rate in the fermion-Green's function, there's a really important effect, which is the heart of this whole story. You notice here that the inelastic scattering rate for the electrons has two contributions, the G and the G prime. So the G is coming from the interaction which has no disorder. The G prime is coming from the interaction that does have disorder. However, what appears in the transport is only the G prime. So the point is that if I look at these various terms, this term can give you a marginal Fermi liquid in the electron spectrum, but it does not give you a strange metal in the resistivity. It's the G prime that does that job. It gives you both a marginal Fermi liquid in the electron spectral function and the right type of resistivity and optical conductivity. So that's our main result, that the key ingredient in getting strange metal behavior with 1 over omega optical conductivity and linear and temperature resistivity is spatial randomness in the interactions. Okay. All right. So now, of course, we have these coupling constants here. We can try to do a more quantitative job to try to fit the data, and we're working on that. And there's many other things we can look at, including magnetoresistance, cyclotron resonance, nonlinear optical spectroscopy, and we're working on all of that. Okay, so just summarize by showing up this phase diagram then. So the main message of my talk is a pseudogap metal is a condo lattice heavy Fermi liquid plus a spin liquid. This has various instabilities, and the main message of the last part of my talk is that spatially random Yukawa couplings are the key to getting a strange metal behavior. Thank you.
Thank you very much for interesting talk. And questions? Yes, please, Sakai-san.
Yeah. In the first part of your talk, when you derive the effective Hamiltonian consisting of C and F.
Yes.
Can you say anything about the momentum dependence of the hybridization B?
Oh, well, we took a momentum independent B. Yeah.
Is it assumption or?
Well, I mean, yeah, it's a condensate of a Higgs field, and yeah, its phase could change. If your phase change, I mean, you could have near neighbor couplings in principle, but the simplest is to just take it completely uniform. The phase you can gauge away because there's a gauge invariance in the theory. So we choose the gauge in which B is totally uniform.
It's related to the symmetry of pseudogap, right?
You could say that, yeah, but I mean, if you had some phase dependence B here, that would lead to very different T1. So if you're going to choose a completely symmetric Fermi surface in T1, then B is fixed. Then B has some information, yes. So in that sense, it's an S-wave pseudogap. But this is just fitting the data. I mean, we haven't done any detailed numerics to find out what's the best solution. I mean, this is also the solution you get for a condo lattice. If you take a condo lattice of spins coupled to conduction electron, this is the Pierce-Coleman solution. That's all we're using.
Thank you very much.
Yeah.
Questions? Yeah, young back.
So I have a couple of questions. So my first question is, in the pseudogap phase, the solution you described, so there's this the spin liquid side, right, in the arising from the S2 spin.
Yeah.
So in principle, that will contribute to the specific heat.
Sure.
In the
Yes.
pseudogap phase. I mean, it's probably not easy to see, but in principle.
Yeah. So I think the most likely candidate for S2 spin liquid is pi flux, which gives the T squared specific heat. It's very small. I mean, it's not a spin-on Fermi surface.
Okay. So
Yeah,
it's not singular, at least, right?
Yeah. I mean, it's going to give you some, there are various indications of pi flux-like physics in neutron scattering at higher energies, even the insulator. There are various papers that claimed it. Many people claim that pi flux spin liquids give you very good variational energies. So, yeah, but also we know it's the same as the Schwinger boson theory.
Right.
That's something we know now today.
My second question is, sorry, so as a function of doping, so your picture is that...
I have one more comment to your previous question.
Sure.
This F1 layer does have a spin-on Fermi surface in principle, but you get rid of it because of the hybridization. So that's right. But when you're going to the phase transition, when you're doing this phase transition here to the strange metal, then that spin-on Fermi surface, so it's not really spin-on here, it gets revealed.
I see.
It's really a ghost Fermi surface or a hidden Fermi surface. That's from the F1 layer. And that will give a specific heat near the optimal doping point. And we think that's a candidate for the big peak in the specific heat. It's like a factor of 2 peak, which is exactly what you would expect from here. Okay, go on.
So you have this picture that as you increase doping,
Yeah.
and in your construction, the JK by J perp,
Yeah.
that somehow the ratio somehow changes. So what's the intuition behind this picture? That why for the low doping, JK is like bigger than J perp? I mean, in the UV theory,
Yeah.
J perp is always large. So
Yeah, the UV theory
so
it
somehow
is.
the idea is that somehow if you go to IR, somehow this happens, right? So
Yeah, yeah. Well, we've done some simple models of, like if you take this to be SYK model, we can solve all the equations in DMFT type equations, and we do find that that's what happens if you change doping
I see.
at fixed J perp over JK. Yeah, I mean, I think this condo screening is very much, it's very much the physics of having these magnetic polarons, antiferromagnetic background. That's, Eugene talks about it that way. This is the same effect in a different language. Yeah, so do you expect that to happen at low doping? Yeah.
Yeah, thank you. I think there are other questions, so.
Questions? Yes, James.
Thank you, Subir. Amazing.
Thank you.
Can I ask some realist questions?
Please.
So is the F1 fermion a real object? Can we tunnel to it or from it?
Well, it hybridizes with C, so answer is yes.
No, in and of itself, is it a real quantum mechanical object?
I mean, okay. Yes. If you want to show one more answer. Yes.
If I go to a genuine Kondo lattice compound,
Yes, yeah,
then the F state is a real electron.
right.
And one can tunnel to it with a probability controlled by the Fano factor.
Yes,
Okay.
yeah.
So is that situation true here?
So in a real system, the F sites are different from the C sites, so you can find them. You can tune the coupling depending on whether you're near an F site or a C site. Here you can't. There's only one site, the C site. So there is, to zeroth order, the coupling is only to the C when you come in, and then the F is really, there's no direct coupling to the F. Yeah, in the bit.
see.
Yeah.
Well, if you were going to say F was real, then I was going to ask you how big is B?
Well, the B is 30 millivolts, but that's the pseudogap.
B is the pseudogap energy
Yeah,
scale.
yeah, on the antinode. That's what it is.
All right.
Yeah.
So a very interesting question for the experimentalist would be to know,
Yeah.
in this beautiful model, what would be the perturbation to the density of states of
Yeah.
the pseudogap due
Right.
to this concept?
Yeah, I mean, to get this model, you're doing some canonical transformations of the C. So because of the canonical transformation, the physical C is some linear combination of the C and the F. But it's fixed. It's not something I'm able to vary. And is that big enough to give a Fano resonance? Yeah, I think that's something we have to, it's related to these anomalous self-energies that we heard about yesterday, and it may depend on can that frequency dependent show up in some STM? Yeah, I don't think so, but it's not out of the question. Yeah.
So, as I mentioned, the hidden part of Fermi is elusive in general, but we need some direct measurement of the evidence. One example is the cancellation of self-energy, while others, and that kind of measurement is the indirect, but there's other way.
So dark fermions, Scylla fermions, and so on. Lovely idea. Experimentalists are challenging because they don't have any direct relationship.
Yeah, that's the reason why we are proposing how can it be detected in some experimental
I mean,
quantity.
this Fermi surface is a linear combination of C and F. I mean, that's the reason you get the hotspots. In fact, going back to ZX's data, he's getting a big hotspot because even though there was no long-range order in the electron group. And we would say in this theory, that's because of the hybridization between the C and the F. That's why there's a hotspot. Yeah.
Yeah, well, I'm sorry that I didn't talk about the optics.
Yes.
but we can talk privately about it. But the thing that that started worrying me here, I must say, was Andrea Damascelli's talk, who pointed out that along the nodal directions, even for the overdoped direction, overdoped dopings, there's a t square in the 1 over tau in the scattering rate. This. Okay, he didn't mention.
You're talking about the photo emission now.
Yeah, exactly.
Okay.
Is this something that?
I'm talking about this strange metal regime. Yeah, where.
Is this a fly in the ointment for you, or is there some rationalization?
You would get a t squared when you move out of the strange metal into the Fermi liquid. Yeah. So when you go down here, when the boson has a little bit of a gap, you will get t squared. So this is really at some critical point, critical phase, where the boson is gapless.
But he showed it for all dopings also.
Well, okay. I don't. I mean, what about Dan Dessau then? Dan Dessau claimed it's linear in frequency and temperature, right? On the nodal direction.
I was just wondering how much is a single specific momentum also versus the integrated response along the Fermi surface playing a role here?
Well, as long as this G prime disorder is large enough, then it's all over the Fermi surface. Of course, there could be effect from density of states and Van Hove singularities, but those tend to be more in the elastic scattering than the inelastic, right? Yeah.
So ZX.
Thank you for such a clear explanation for a complicated theory. If I would look at this, probably the most salient thing one could test would be to see the difference of the Fermi surfaces pocket in the pseudogap phase being half of the ordered phase. And these will also be true in the electron doped system. Yeah.
I mean, it has to do with the backside being along this line, not, I mean, if you imagine that, I mean, this was actually, I think Seamus in particular, I remember you would draw the arcs and then make it flat, and then you would say this area is P. Then that means it is really flat. Whereas on the other hand, if you look at what Takeshi is doing, he's taking the full ellipse and saying that area is P. And that is what is observed. And that's consistent here even with quantum oscillations. So there is some evidence that this shape is changing. In this case, the backside is flat, and in here it's not.
Right. So far, in the electron doped one will be more similar to what Takeshi has seen.
Yeah.
So,
I misstated something. Yeah. This area, the full area, is not P. It's 2P actually, because the Brillouin zone. So, I'm sorry, I misstated that. Here also, if you just take the half, you'll get P. It's just that the backside is at a different place. Yeah. But here, when you don't have magnetic order, there's no sense in which the magnetic Brillouin zones is there. So it's not as, these are realistic pictures for calculation. It's not doubling in size, it's just where the backside is. So of course we'd love, in the end, the smoking gun is to see this backside.
Technically, of course, the former is harder because it's getting closer in momentum space. Your momentum resolution makes it harder. It's very clear that one thing is a very unambiguous prediction in that sense. To test.
Well, okay. Just seeing this large gap in your data at the hotspot already is is pretty exciting, but all right. Maybe it's not a smoking gun.
So in your, maybe I missed, but in your theory of strange metal in the last part, does it give Planckian dissipation or?
Yes. So I can tell you a little bit about that. I didn't go into that. but it's related to this. So when people talk about Planckian dissipation, you take some transport rate and you divide it with some effective mass that comes from some one electron property or the specific heat, for example. So the key point here is that the transport involves G prime, and the effective mass involves G and G prime. Now, if you had a theory where G was 0, where the coupling was completely random, then we do get exactly Planckian behavior with a coefficient of pi over 2 or something like that. Not so far from what's seen. But in the full theory, what you would expect is this alpha parameter, that's 1 over tau is alpha times kt. Alpha is G prime squared divided by G squared plus G prime squared. So it can become much smaller, but there's a maximum, which is when G goes to 0, or G prime is much bigger than G. Yeah. So short answer is yes. I didn't discuss it, but there is Planckian behavior here.
Yeah, related to this question, so the Planckian fluid is related to the quantum entanglement and degree of quantum entanglement. And if you introduce randomness, how is that entanglement change?
Okay, so if it's the question how you measure entanglement, one way to measure is by this out-of-time autocorrelation function, for example.
Yeah.
Yeah. So we have a paper on the pure system where G prime is 0. This came out in PRL with Avishkar Patil and Maria Tikhanovskaya. And there we show that it has a maximal OTOC 2 pi kt over h bar growth rate. We are finishing a paper where we take the random case, and it's also almost maximal with some weak log corrections. Well, so it doesn't affect any, you know.
Well, but in some intuitive picture, if you introduce randomness, because of some frozen effect or classical effect, I suppose that the entanglement may...
Well, not necessarily. I mean, the SYK model is completely random and it's maximally entangled. But I would say that if you had localization, then if randomness was strong enough to introduce localization, then you lose the entanglement. However, the whole central idea of strange metal is that inelastic processes dominate completely, and that cuts off localization. There are some rare region effects we still have to think about, but localization gets completely cut off. So the entanglement is not much affected by impurities. Yeah.
Can we call that Planckian glass, or?
It's a quantum liquid more than a glass. Yeah.
Okay. Are there any other questions?
I would call it an SYK liquid, but okay.
Other questions or comments? Fujimori-san.
Thank you very much for the very interesting talk. May I come back to the Fermi surface?
Yes.
So top figure, the backside of a Fermi surface is not exactly the straight line.
No, it's not exactly straight. So that's one difference from the YRZ theory.
But so it depends on the form of B.
Yeah, so we just took, like I said, we fit the data, and we just took...
you assume the B is a constant.
B is a constant, and we have 4 fitting parameters. B, T1, well, the first, second, third neighbor of T1, that's it.
So it depends on the symmetry of the pseudogap, D-wave type or
I'm not sure what you mean by symmetry of the pseudogap. In the end, for gauge invariant observables, there is no broken symmetry. There is, so we're certainly saying that any physical observable has the full symmetry of the square lattice in the pseudogap.
I just wondered, by measuring the backside of the frame surface, you can determine the symmetry of the pseudogap. No.
Well, I think the whole concept of symmetry of a pseudogap is a bit gauge dependent. It's not an absolute concept. Unlike D-wave pairing, that's not gauge dependent. There's a gauge invariant autoparameter there. I don't think there's any such thing here.
Yes. Last question.
Staring at this, I was wondering, what would be the spin susceptibility? Is there a sharp distinction between the p-type being incommensurate and the electron type being commensurate? This picture would say things looks like commensurate, or it's everything you predict what Bernhard was pointing to is locally they are always incommensurate.
Yeah, I don't think there'll be much difference. I mean, we're really at higher temperatures here, and you're just getting the Pauli susceptibility and various Lindhardt functions from here. There is the second layer, which I haven't discussed much at all, and it could be that on the p-type, the second layer is completely commensurate, and the n-type, the second layer is commensurate, but the susceptibility, spin susceptibility from that, at least the uniform susceptibility is very weak. Yeah, for neutron scattering, you could, in principle, see this.
Yeah.
So there we just mean, so what we're saying is that there are two contributions to neutron scattering. One is the usual chi of q and omega that you get from the Fermi surface. And the second is a contribution that you'd get from the S2 layer. And you just add them up. And I think there's a lot of evidence in neutron that there's some collective excitation that have nothing to do with Fermi surfaces, but okay.
Yeah, but the phenomenology of the low-line excitation in the neutron, the distinction between the two classes,
right?
Pretty striking.
Yeah, I agree. Yeah, I agree. We should try to understand that.
I'm sorry that time is pretty over, and actually I have also several other questions, but let me discuss later. So time is actually pretty much over. So first, let's thank our speaker again. Very nice talk. So the next session will start 10 minutes later than